Welcome back to the Math Professors. If you're looking for content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and we're going to cover the Dirac delta function. So, a differential equation topic that happens near the end of your first course in differential equations, and it really has two properties. We say that the delta Dirac function is it's infinity when t is equal to a, and it's 0 when t is not equal to a. And what I've done is that I've graphed it over here, so we can see that it's 0 everywhere except this a value. Now, this is also called the impulse function, and what we can kind of think about this is in physics, if we hit something like if I want to hit a golf ball, for instance, what we have is we have a very large force over a very small amount of time, and this is very useful for us when doing this in physics, as opposed to the unit step function, which really is applying a constant force at a particular time. So this is considered the impulse, big force over very instantaneous time, as opposed to this one, which could be a constant force, starting at time a. So the other property is we say that the integral from 0 to infinity of this Dirac delta function is equal to 1. Now, it's strange for us to have this y value of infinity, but that's just kind of by definition what this is. All right, so note that the derivative of your unit step function actually is equal to this Dirac delta function. So here's a theorem that's going to become useful for us when we're trying to find solutions to differential equations, involving these things. So the Laplace of that delta Dirac, or the Dirac delta at t minus a, is going to be equal to e to the minus sa. So the example here is, what is the Laplace of the Dirac delta function, shifted over 3 units? Well, this is going to be equal to, this is going to be your a, so this is going to be e to the minus s times 3, or I can say minus 3s. So let's use this for solving differential equations. All right, so here's our example. I want to solve this second order differential equation, and what we know is that it's not homogeneous. It's actually equal to 4 times the Dirac function. So what we're going to do is we're going to Laplace both sides of this thing. So I'm going to Laplace this side. I'm going to Laplace this side. And I'm just going to go ahead and pull out that 4. Okay, so now we know the Laplace of a y double prime is s squared capital Y of s minus s y of 0 minus just y prime of 0. And then the Laplace of y is going to be plus r capital Y of s. Now over here I'm going to have 4 times the Laplace of this, and now we know that this is going to be e to the minus s times a. In this case, a is going to be 2 pi, so minus 2 pi s. Now we can plug in our initial conditions. So y of 0 is equal to 1, so this will just be equal to 1. And then y prime of 0 is going to be equal to 0, so that'll cancel. So what we're going to get here is s squared y of s minus s plus y of s is equal to 4e to the minus 2 pi s. Now remember, we've taken the Laplace of this. It's algebraic. I just have to solve this for capital Y, and then eventually take the Laplace inverse. So sending this s over, and then divide, well, I'm going to factor this out. I'll do all the work. Is equal to that side. So then finally, capital Y of s is going to be equal to this over s squared plus 1. Plus s over s squared plus 1. So now that it's solved for this, I have to just take the Laplace inverse of both sides. All right, so I know I can pull out this 4. It's a constant linearity. And this one I already know, we've done enough of this, that this is the cosine function. So this is going to be plus the cosine of t. Now, what this is this e to the, let's clean that up so we can see that a little bit better. This e to the minus 2 pi s really is the shift of the Laplace that this is multiplied by. So what this is this is, you know, the Laplace inverse of, you know, 1 over that s squared plus 1 shifted by, you know, 2 pi. And what I know is that this is the sine of t. So what this is going to be is this is going to be equal to 4 times the sine of not t, but shifted, so t minus 2 pi. Now, oh, I forgot to multiply this by that unit step function, and it also turns out at that spot, so t minus 2 pi. And this is, of course, plus the cosine of t. We could also write this in terms of its of a piecewise function if we choose to as well. And we might as well pull that off just to make sure that this makes sense. So what I know is that it's equal to this cosine function all the way up till we get to this 2 pi. So I know from 0 less than or equal to t less than 2 pi, it's going to be equal to this cosine function. A lot of times we might write this cosine function in front. And what we know is that this unit step function will turn this function on at that particular number. So it starts out with a cosine function. And then what it's going to do is it's going to turn on this function at 2 pi. So it's going to turn on that 4 sine of t minus 2 pi at, you know, 2 pi. So this is going to be greater than or equal to 2 pi. Now what I do know is that the function is periodic at 2 pi, so t minus 2 pi is also just the same thing as the sine of t, so I could just write it this way if I choose.